This presentation describes RanKloud, a scalable multimedia data processing system developed here at Arizona State University. This work is a joint effort of Professor K. Selchuk-Kandon, Jong Kim, Parth Nagarkar, Mithila Nagendra, and Renwei Yu. So what is the need for such a system? Today, data is produced in massive quantities. The application diversity is matched by the need for processing of data with diverse characteristics, including quality of capture and variable precision in representation. All existing systems treat data elements as if their contributions to the overall data analysis were identical. However, in many applications, features extracted from data have varying accuracy. Thus, for the next generation massive data analysis middleware to have transformative impact, the fundamental principles that govern the design must include data and operator imprecision and relevance of data to a particular analysis task. An example of a framework that can be used for large-scale data processing is MapReduce. MapReduce, the popular large-scale data processing framework, is based on a functional list processing language. The user-provided map and reduce primitives can be parallelized and combined into complex data processing workflows as shown in the figure. The MapReduce framework has been shown to be very effective in the implementation of real-world tasks such as web link analysis, web access log analysis, document clustering, and retrieval. In systems that use MapReduce, common split strategies include random and key range-based partitioning. These don't take into consideration the variable in precision or the quality of data, as RanKloud aims to do. When the utility assessments of the media objects vary, users are often interested in having results being ranked according to a given utility criterion, and only the best matches are returned as the search result. This is commonly referred to as ranked or top K retrieval. Most rank processing systems include the basic operators shown on the slide. These are K nearest neighbor, K best nearest neighbor, top K retrieval, Skyline, and top K Skyline retrieval. Now let us take a look at an example top K join query on sample multimedia datasets. Given two datasets, color match results and texture match results, the given query would return the best 1000 images based on the average of pre-computed color and texture matching scores. The 0.95 indicates the confidence lower bound. This means that there is less than 5% chance that the result set will include less than 1000 results. In this presentation, we focused on the challenges that we faced in parallelizing top K queries on batch-oriented cluster architectures. Implementing rank processing operators over a system that partitions the data and processes the partitions in batches requires care. Often, naive partitioning of the data onto servers will waste resources. It will incur data replication costs. If an index structure is used, it will incur cost of indexing and accessing these index structures. And lastly, the system will use resources for producing large number of local candidates that will eventually be eliminated when the results from all the servers are combined due to their low global utilities. As you can see from the above figures, relying on sorted and random access operations, existing top K join algorithms try to focus on the high utility corner of the utility space. Here, in figure A, the curve represents the boundary defined by theta K. The lowest of the scores of the best K results, any candidate result below this threshold needs to be pruned. B represents random partitioning of the data, and it shows that it will result in waste of resources for producing large number of candidates that will eventually be pruned. This slide illustrates the main idea behind RanKloud. Our top K operator first estimates the cutoff theta K and then partitions the useful work above the threshold to the available servers in the cluster. This can significantly reduce the redundant work done during top K processing. To give another example of a ranked operation on RanKloud, we look at the Skyline operator. As you can see from the figures, similar savings in processing time can be obtained in Skyline joins if work can be partitioned in a waste-avoiding manner. Here, in figure A, You can see that very few results from the first 3 servers will be needed for the calculation of the global skyline if the work is partitioned in a grid manner. But as figure B shows, if the work is partitioned in a utility-aware manner, there will be less redundant work as compared to naive work partitioning. We won't talk about the Skyline operator in the next few slides, but only focus on top K processing. My colleague will now explain uSplit, the utility-aware partitioning method that is used by RanKloud.
Due to the simplicity of the MapReduce framework, it provides opportunities for significant degree of efficiency batched parallelism. RanKloud, which is implemented over Hadoop, parallelizes the linked processing operations like a top K join by building on the MapReduce paradigm. It uses utility-based partitioning and resource allocation schemas based on 2 main criteria. Criteria A, wasted work criterion. This takes into account how much of the system resources are allocated to produce results that are not in the top K. Criteria B, partitioning work balance criterion. Any imbalance in the work assignment means that certain system resources are stay underutilized, which others are overutilized. We refer to this utility-aware data and work partitioning process as uSplit. In uSplit, our challenges include on how to accurately estimate a corresponding utility boundary. This ensures that only the data with the higher utility and the possibility to be in the top K will be accessed. We also need to split the work among the servers such that the work is balanced. As seen before, we don't want one server to do most of the work and the others do only partial amount of the work. And there will be some servers which will have some data that will be below the corresponding utility boundary. So this needs to be avoided in such a way that the server only accesses the data above the boundary. The above figure shows the steps of the join process. Step A, RanKloud first estimates the join selectivity as a function of the input data utilities, and then Step B computes the lower bound theta k on the utilities of the top K results based on these selectivities. Next, Step C, RanKloud estimates the amount of useful work needed for computing the top K results. And based on this estimate, Step D, it partitions the input data in a work-balanced manner before assigning these partitions onto the available servers for processing. Step E, each server creates the necessary data structures and performs the assigned portion of the join task. Finally, Step F, the results from the individual servers are combined to select the best K results. Since the estimation of theta K is based on available statistics, RanKloud also takes into account a confidence target of obtaining K results. Naturally, the amount of work will depend on how tight this confidence target is.
My colleague has talked about the challenges in parallelizing top K queries and also described uSplit. Now I will talk about the 3 key contributions that we have made through RanKloud. Our first one is adaptive sampling. In traditional sampling, samples are collected uniformly from the utility space. In our adaptive sampling, we sample more in the higher utility space since precision of the predictions of the amount of work is more important. RanKloud's second key contribution is the lower bound estimation. As explained before, given a query task of top K, we estimate a lower bound threshold according to given statistic information. This ensures that only the data with higher utility and the possibility to be in the top K will be accessed. Our another key contribution is workload balance partitioning. In this figure, assuming there are 5 servers, we split workload in such a way that all servers do equal amount of work. For further information regarding these statistic collection steps and partitioning, please check our technical report. For evaluation purposes, we compared our uSplit strategy with Vertica's limit K option. Vertica is a commercial database. This slide shows example experiment results. We used datasets with different characteristics and sizes. We created synthetic uniform datasets with 500 million data elements, 14 GB per source. The experiments were executed on Amazon EC2 with 10 Red Hat CentOS 5.2 machines. As you can see from the above figures, using uSplit we can finish query tasks much faster than just using Vertica. For example, given a query task for top 100 million, after using uSplit we can achieve a speed up of almost 10 times. Vertica finishes this task in approximately 6 hours, while after using uSplit the task only requires around half an hour. More extensive evaluations can be found in our technical report. The following is the top K join query that we have used in the demo shown in this presentation. We have two tables, dataset 1 and dataset 2. They have two columns of document ID and sentence score. The top K join query returns the top 100,000 documents which contains highest scoring sentence pairs. The K is 100,000 and 0.95 is the confidence lower bound, which means that there is 5% chance that the result set contains less than 100,000 results. This is our top K join workflow. We have written optimization parameters instead of all the parameters that we have for the reader's convenience. If the reader wants to know more about these, please check our technical report. We have two datasets as inputs and we have 6 steps in this query to perform the top K join. In the initial 2 steps that you see on the screen, the sampler collects the necessary information for estimating the data statistics as explained in the previous slides. The first 2 steps were about sampling the datasets. In this step, the calc selectivity estimates the join selectivity of the datasets from the histograms obtained from the sampler. The next step involves the computation of the lower bound theta k based on the join selectivity from the previous step. The operator performs the last 2 steps. The build index step creates the index of the dataset on the key value pair mentioned by the user. Our system is connected to Berkeley DB, which creates the index on each server using the lower bound theta k. And in the last step, the top K join takes place. The user can input the number of K values that he wants. The merge function, for example, we have used average in the next experiment, and the theta value that was outputted from the previous step. The final result is stored on the HDFS in the folder called query result. This is the actual user-defined query script that is run during the demo. The K here is 100,000. The datasets are of size approximately 3.7 million and 950,000. As explained in the previous slides, every step performs a specific function, and each of these steps can be carried out individually in the specific order. For example, if the user wants to run another query on the same dataset, and if one of the datasets has been indexed before, the user can comment out the indexing step. The user can reuse the index that was built in the previous run rather than rebuilding the index once again. In our demo, we use 2 datasets. Both these datasets need to be first copied to the HDFS. This step is not shown here. Right now we are sampling the first dataset. It has approximately 3.7 million tuples in it. The format of both the datasets is the same from the top K join query as explained before. This sample demo was carried out on a Hadoop cluster that contains 2 servers. One is the master and the other one is the slave. These servers have Intel Core 2 Duo processor with 2 GB memory on Ubuntu 9.04 OS. It is important to note that we have carried out extensive experiments on clusters that contained 10 to 20 servers. As mentioned earlier, this can be found in our technical report. Since there is only one file in the input folder for the first dataset, the total input paths to process is 1. The second dataset contains approximately 950,000 tuples. Similar to the previous step, this dataset is also sampled. The input path to process is again 1. Since the size of the second dataset is comparatively smaller to the first dataset, this step takes around 35 seconds, which is approximately 25 seconds faster than the previous step. Now let's wait for the sampling of the second dataset to finish. Now the joint selectivity of the datasets is being estimated. This step takes less time than the next step where theta is calculated. It takes around 47 seconds to calculate it. Theta is the lower bound cutoff above which we expect at least k results to be present. This step requires the outputs from the sampling step and the previous step calc selectivity. This step outputs a file on the HDFS with the estimated theta value. This theta value, as you will see, is used in the build index and the top k join steps. Now let's wait for the theta compute step to finish. The next step is the index creation step. The index is built in parallel on both the servers in the cluster. B-tree index structures are created on the local disk of both servers. The B-tree index has a composite key that is formed by the join attribute and the utility score. We use BerkeleyDB to do this. The user gets to specify the dataset on which the index needs to be built. We have chosen the second dataset in this case. The map indexing step has an overhead of around 25 seconds. This is caused by the map initialization that is carried out by Hadoop. We still do this through the Hadoop framework as it builds the index on each server in the clusters in parallel. The actual indexing process takes around 38 seconds for the second dataset. This indexing step is critical and necessary since it enables the join processing to be carried out efficiently and in parallel. Now we come to our join processing and the top k selection step. Here the potential results about the cutoff theta are joined. The first dataset is read and the tuples are split into workload balanced partitions using our partitioning method that is called by Hadoop before the join processing takes place. These partitions are processed in parallel by the join operator. In the map phase, the tuples from the first dataset is read by Hadoop, and the actual join process takes place in this reduce phase, as you see. Once it reaches 100%, we have to go through another MapReduce phase. This phase is carried out in order to select the top 100,000 results. These results are stored on the HDFS in a user-defined folder called query result in this case. The results can be copied to the local disk or displayed on the console using cat. Hadoop has an inbuilt copy to local command to copy them on the local disk. As you can see, we have catted out all the 100,000 results. This step requires about 83 seconds to complete. This brings us to the end of our presentation. Thank you for listening. All details of the uSplit component of our RanKloud framework can be found in the technical report. It can be downloaded from the link shown in this slide. Thank you once again.